56,000 pounds. That's the load sitting on a single tire of a Boeing 777 as it touches down. 28 tons on one wheel. And the patch of rubber actually touching the runway, the part doing all the work, is about the size of a kitchen cutting board. Now look at that tire. It's bald. No tread blocks, no chunky grip pattern, nothing like the tires on your car. Just a smooth black ring with a few shallow grooves cut around it. It looks cheap. It looks worn out. It looks like the last thing you'd trust under a $500,000 airplane. And here's the part that should stop you. A third of a second after it hits the runway at over 170 miles an hour, that bald tire is hot enough to vaporize its own surface. You've seen the puff of white smoke at touchdown. That smoke is the tire boiling. And it does not catch fire. It is engineered deliberately not to. So how does a small, bald, ordinary-looking rubber ring hold up 500 tons of jet, survive being slammed from 0 to airliner speed in a fraction of a second? Refuse to burn when it's hot enough to, and this is real. Come with a hole drilled into every wheel so it can blow itself up on purpose. By the end of this video, you'll understand 4 impossible jobs this tire does on every single flight. You'll meet the engineers who figured it out. A 17-inch strip of titanium that destroyed the safest aircraft ever built, and a maintenance supervisor who wouldn't wait for a tank of nitrogen. A decision that killed 261 people. And you'll learn the one secret that ties all of it together. Because the tire that holds up the jet, the tire that won't burn, the tire that survives all of it, the answer is the same. It was never the rubber. Start with the impossible part, the weight. A fully loaded Boeing 777-300ER weighs around 775,000 pounds at takeoff. It rolls on 14 tires, 2 at the nose, and 12 on the main gear, split into 2 6-wheel bogies, 1 under each side of the fuselage. Do the math on the main gear, and each of those tires is carrying tens of thousands of pounds. A Boeing 767 main tire is rated to 51,000, a 777 tire, more. Your instinct says the tire should be enormous. A pillar of solid rubber, it isn't. It's barely taller than a person, and it's mostly hollow. So what's holding the plane up? Not the rubber, the pressure. A car tire runs at about 32 pounds per square inch. A 777 tire runs at around 215, roughly 6 to 7 times higher, and that number is the entire trick. There's a simple relationship engineers use. The contact patch area equals the load divided by the pressure. Push 51,000 pounds down onto a tire, inflated to 205 pounds per square inch, and the rubber flattens out until the footprint is just big enough to carry it. About 250 square inches, a cutting board. So when you press down on that tire, you are not really pressing on rubber at all. You're pressing on a column of compressed gas. The rubber is a skin stretched over a bottle of pressure, and the pressure is what's load-bearing. Make the gas stiffer, and you don't need a bigger tire. You need a tougher bottle. Here's the proof of how far that scales. The Airbus A380, the largest passenger jet ever built, weighs over 1.25 million pounds and rides on 22 wheels. Each main tire is designed to carry nearly 60,000 pounds. And the Antonov 225, the largest aircraft that ever flew, spread its weight across 32 wheels. Not because the rubber couldn't take more, because the runway couldn't. That's job 1. It was never the rubber, it was the gas inside it. Now the part everyone gets wrong, the bald look. People see those smooth tires and assume the airline is cutting corners, running them till they're worn flat. Your instinct is reasonable. It's also exactly backwards. The tire is bald on purpose, and the reasons are some of the best engineering on the entire airplane. Picture the moment of touchdown. The wheel is completely still. The runway underneath is moving at 170 miles an hour. The instant rubber meets pavement, the contact patch is being dragged sideways at the full speed of the airplane, while it spins up to rolling speed. Now imagine your car tire's chunky tread blocks in that moment. Those blocks stick out, they have free edges. Drag them across concrete at 170 from a dead stop, and they don't grip. They tear off. so aircraft tires don't have them. What they have instead are continuous ribs running all the way around the tire, with no loose edges to shear away. The grooves between those ribs do two quiet jobs. They channel water out from under the tire to fight aquaplaning on a wet runway, and this is the part nobody tells you, they're wear gauges. The manual says retire the tire when the wear reaches the bottom of a groove. The grooves aren't there to grip. They're a built-in ruler telling the mechanic when the tire is done. And the grip thing, flip your intuition one more time. An aircraft tire isn't trying to grip the way a sports car does. The anti-skid braking system actually wants the tire to slip. A little. It brakes hardest at around 10 to 15% slip. A smooth, ribbed tire brakes better than a blocky one, because it spreads heat evenly instead of concentrating it where chunks can rip loose. So the tire is bald because grip would get it killed. It doesn't grip, it endures. It was never the rubber. Here's where it gets violent. Touchdown speed for a big jet, what pilots call the reference landing speed, runs roughly 130 to 170 knots. That's 150 to nearly 200 miles an hour, and at that speed, the wheel hits the runway, not spinning at all. It has to catch up. 0 to over 900 revolutions per minute in about a third of a second, while the plane skids forward roughly 10 meters down the runway. In that instant, the friction at the contact patch is enormous. A NASA study measured a locked sliding wheel absorbing the equivalent of 460 horsepower of friction energy through a patch of rubber smaller than a sheet of paper. The surface temperature spikes toward 260 degrees Celsius, 500 Fahrenheit, in a third of a second. That's the white smoke. And here's the reveal. It is not fire. The rubber isn't burning. It's flashing straight from solid to vapor. At around 200 degrees, the rubber surface starts boiling off as a cloud of vaporized particles, white smoke, not flame. The tire is sacrificing a microscopically thin layer of itself to survive the heat. Every landing, each tire leaves about 1.5 pounds of itself behind on the runway. A single A380 landing can smear 14 kilograms of rubber across the touchdown zone. At a major airport, crews scrape up thousands of kilograms of boiled-off tire every single day because it builds up so thick it becomes a hazard of its own. So why not just spin the tires up before landing and skip the skid entirely? People have asked that question for 70 years. Engineers studied it, tested it, and rejected it. 3 reasons. The rearward jolt of the spin-up is actually built into how the landing gear is structurally designed. Take it away, and you have to recertify the gear. Spin-up motors add weight, cost, and brand new ways to fail. And here's the kicker. The skid barely matters for tire life. Almost all the wear comes from braking during rollout, not from that violent third of a second. So they left the slam in, they just built a tire that eats it. That's job 2. The tire doesn't avoid the abuse, it's designed around it. And it was never the rubber, it was the cords and the compounds underneath. So the tire is hot enough to vaporize. Why doesn't the whole thing catch fire? Part of the answer is the heat is brief, and the rubber is engineered to boil instead of combust. But the real answer is hiding inside the tire. It's not filled with air, it's filled with nitrogen, and that choice is written in blood. March 31st, 1986. Mexicana de Aviación, Flight 940, a Boeing 727, takes off from Mexico City for Los Angeles. A jammed brake on the center gear overheats the tire next to it. That tire had been filled with ordinary compressed air. Air is about 1/5 oxygen. Heat the rubber enough and it releases flammable gases. And inside that tire, those gases met oxygen under high pressure and detonated. The tire exploded in the wheel well. It cut fuel and hydraulic lines. The fire spread. The 727 came apart over the mountains. All 167 people on board died. The lesson was brutal and simple. Oxygen is the enemy, so regulators banned it. After Mexicana, the FAA issued an airworthiness directive requiring the gas inside the tires of large aircraft to hold no more than 5% oxygen. By 1993, it was federal law. Every aircraft over 75,000 pounds with braked wheels must inflate its tires with dry nitrogen, or another inert gas. Nitrogen doesn't burn, it can't feed the fire, and as a bonus, it's dry. No water vapor to corrode the wheel or to make the pressure swing unpredictably as the tire roasts on landing and freezes at altitude. So the tire refuses to catch fire for the same reason it holds up the jet, because of what's inside it. It was never the rubber, it was the nitrogen. But nitrogen alone isn't enough, because there's still the heat from the brakes, and so engineers did something that sounds insane. They drilled a hole in every wheel and designed the tire to blow itself out, on command. It's called a fuse plug, a small bolt threaded into the wheel, with its center filled with a metal alloy that melts at a precise temperature. When the brakes overheat, say after a rejected takeoff, when a pilot slams on everything at full speed and dumps enormous energy into the discs, the wheel temperature climbs. Hit the trigger point, and the alloy in the fuse plug melts, the plug opens, and the tire deflates slowly and on purpose through that hole. Think about why that's brilliant. An overheated tire at 200 pounds per square inch that bursts on its own throws shrapnel. It can sever a fuel line, shred the next tire over, punch through structure. A controlled deflation just goes hiss and sags flat. It's the exact same idea as a fuse in your home's electrical panel. You build in the weakest point deliberately, so that when something overloads, it fails where you chose, the way you chose, instead of taking out everything around it. There's a whole aerospace standard governing these plugs. There are patents going back decades, one from Goodyear's aerospace division, specifying an alloy that melts within 1 degree Fahrenheit of its target. That's the level of precision on a part whose entire job is to fail. That's job 3. The tire is engineered down to a single degree, to destroy itself before it can hurt anything else. It was never the rubber, it was the fuse. So if the rubber is just the skin, what's actually doing the work? Peel a commercial aircraft tire open, and it looks less like a tire and more like a woven pressure vessel. At the very edges, where it grips the wheel rim, are bundles of high-tensile steel wire, the beads, clamping it down so 200 pounds per square inch can't blow it off the rim. Wrapped through the body are layers of cord, nylon, aramid, the same family of fiber as bulletproof vests, laid at crossing angles, layer over layer, each one adding load capacity. Then, breaker plies to spread stress. Reinforcing fabric under the tread, heat-resistant under-tread rubber, a chafer strip at the bead, and an airtight inner liner sealing the gas in. The rubber you can see is the thinnest part of the story. Underneath is rope and wire and steel. And it got smarter. In 2001, Michelin introduced a technology called near-zero growth. Built first for Concorde, now standard on the A380 and A350. A normal tire balloons slightly when you inflate it. Near-zero growth uses ultra-high tensile composite cord, so the casing barely grows at all. That cuts the tension in the tread, makes it tougher against debris, and remember this detail, makes the tire break into small harmless fragments if it's destroyed, instead of launching one big lethal chunk. Hold on to that. It's about to matter more than anything else in this story. It was never the rubber, it was the architecture. Before any of this flies, the tire has to survive a certification process designed basically to murder it. The governing standard is the FAA's Tire Certification Standard, and the tests are not gentle. The headline one: the tire must be inflated to 4 times its normal pressure and hold for 3 seconds without bursting. For an A380 tire that normally runs around 220 pounds per square inch, that means pumping it up to nearly 900 pounds per square inch of hydraulic pressure and watching to see if it explodes. Then, they keep going past that, until it finally does burst, just to map exactly how much margin is really there. Then, they spin it. Tires are run on a dynamometer through dozens of takeoff and landing cycles back to back, plus deliberate overload cycles at 50% above rated load, at or beyond their rated speed. And for the biggest jets, that rated speed is 235 miles an hour. faster than almost any car will ever go, on a tire that's about to be told to do it again, and again, and again. That's the bar. Survive 4 times your own pressure. Survive overload. Survive over 200 miles an hour on a drum. Only then do you get to carry people. It was never the rubber, it was everything we proved it could take. Here's a fact that should not be true. The aviation industry obsesses over every single gram of weight. Engineers will redesign a bracket to save an ounce. And yet, roughly 80% of the commercial aircraft tires flying in the United States right now are retreads. Recycled, stripped, and rebuilt. A jet tire lasts only a couple hundred landings before the tread is gone. But the carcass, that woven cage of steel and cord, is far from finished. So they buff off the old tread down to the casing, inspect it with X-ray and ultrasound for any hidden flaw, bond fresh rubber on, and cure it back into a mold. A single casing can be retreaded several times before it's finally condemned. It's not patching a tire, it's resoling a boot. The leather's still good, you just replace the sole, until one day the leather isn't, and you throw the whole thing out. It works because, again, the part that matters was never the rubber. It's the cage underneath, and the cage outlives the tread many times over. A new wide-body tire can cost $5,000 or $6,000. A retread, half that. Across the industry, it saves over $100 million a year. The most weight-obsessed industry on Earth flies on recycled rubber. And it's perfectly safe because the rubber was never the point. Now, the disaster this entire video has been walking toward. Because for all that engineering, there was a scenario nobody had required the tire to survive. And on one afternoon in 2000, it killed the safest aircraft in the history of flight. July 25th, 2000. Charles de Gaulle Airport, Paris. Minutes earlier, a Continental Airlines DC-10 had taken off from the same runway and, without anyone noticing, shed a thin strip of titanium from one of its engines. 17 inches long, 1.5 millimeters thick. It lay on the runway like a dropped ruler. Then Air France Flight 4590 began its takeoff roll. A Concorde, an aircraft that in 27 years of service had never had a fatal accident. 100 passengers, 9 crew. At around 185 miles an hour, the Concorde's left main tire ran straight over that titanium strip. The strip sliced the tire open and it burst. And this is the cruel part. A 4.5 kilogram chunk of tire, one big piece, was hurled upward at an estimated 300 miles an hour into the underside of the wing. It didn't even puncture the fuel tank directly. It hit so hard, it sent a shockwave through the fuel inside, and the tank ruptured from the inside out. Fuel poured out, ignited, and the Concorde lifted off already on fire, unable to climb, unable to accelerate. It came down on a hotel in Gonesse. Everyone on board, 109 people, and 4 more on the ground. 113 dead. The investigators found something uncomfortable. The tires met every standard in force. The certification rules simply never required a tire to survive a strip of metal lying on the runway. It was a missing test, a scenario no one had imagined until it happened. And the fix is the detail I told you to remember. When Concorde returned to the sky, it flew on Michelin's new near-zero growth tires. The ones engineered to shatter into small, harmless fragments. Instead of throwing one lethal chunk, the tire that ended Concorde and the tire that brought it back were the same part, reimagined so that when it failed small. That near-zero growth design is now standard on the A380 and the A350. The 2 largest Airbus jets in the world fly on a lesson learned from 113 deaths. And if Concorde shows what happens when nobody saw it coming, this last one shows what happens when somebody did, and went anyway. July 11th, 1991. Jeddah, Saudi Arabia. A DC-8 chartered to fly 247 Hajj pilgrims home to Nigeria. Before pushback, the lead mechanic checks the tires and finds 2 of them on the left main gear, dangerously underinflated. He wants to fix it. but there's no nitrogen readily available to inflate them properly, and inflating them means a delay. The project manager, unwilling to accept that delay, overrides him. The plane is cleared to go. Here is the chain that one decision set off. An underinflated tire can't carry its share, so it dumps its load onto the tire next to it. That tire overheats, overflexes, and fails early in the takeoff roll. The friction of the dragging wheel starts a fire, a real, self-sustaining fire on the gear during takeoff. And then the crew, not understanding what was burning beneath them, raised the landing gear. They pulled the fire up into the wheel well, sealed it inside the fuselage right next to the fuel and hydraulic lines. Investigators later concluded that if they had simply left the gear down, the accident might have been survivable. It wasn't. The DC-8 became uncontrollable and crashed less than 2 miles short of the runway. All 261 people on board were killed because 2 tires were a few PSI low, and nobody would wait for a tank of nitrogen. It was never the rubber, it was the pressure inside it. And the moment a human being decided the pressure didn't matter. So go back to the beginning. 56,000 pounds on one bald tire, on a footprint the size of a cutting board. You know now why it can hold that. Not the rubber, the column of nitrogen inside it, stiff enough to turn a thin skin into a structural pillar. You know why it's bald, because grip would tear it apart, so it endures instead. You know why the white smoke at touchdown isn't fire, but the tire boiling off a sacrificial layer of itself in a third of a second. You know why it won't explode, the inert gas that replaced the air after Mexicana, and why every wheel has a fuse drilled into it, engineered to fail at a single degree so it never fails catastrophically. You know it's woven from steel and aramid and cured 4 times over, tested to 4 times its own pressure, and recycled by the most weight-obsessed industry on the planet. And you know the 2 times we forgot what it really was. A 17-inch strip of titanium that turned 1 tire into 1 lethal chunk over Paris, 2 underinflated tires, and a manager who wouldn't wait over Jeddah. Every safety rule on that bald little ring is written in the names of people who died teaching us to respect it. Next time you're at the window seat and you feel that thud and see that puff of smoke, look closer. That's not a worn-out tire scraping the runway. That's a pressure vessel, woven from wire and rope, filled with inert gas, hitting the ground at 170 miles an hour and shrugging it off, exactly as designed. Because the one thing it was never about, the black, bald, ordinary thing you were looking at the whole time, it was never the rubber. So here's the question to sit with. The single most abused, most over-engineered, most blood-earned component on a $500 million airplane is also the one part every passenger walks past without a second glance. What else are you trusting your life to right now and not even seeing?